Hi, my name is Datis, and today we will be talking about Virtio, standing for Virtual Input/Output. In this video, we're going to talk not only about Virtio, but before that, we need to discuss how your operating system even runs, QEMU, and how it makes your operating system run, where Virtio fits into the picture of all of this, and some examples of how an operating system will use Virtio to communicate with devices. So, with that in mind, let's just get right into it. So, we must first do some setup before we dive fully deep into Virtio. Your operating system uses RISC-V. That means that when you compile down your C code, it gets turned into RISC-V assembly. And when you do your later parts of your MP where you're writing prep sections or parts for threading, you're just going to be writing full-on assembly. The issue is that this requires a RISC-V based CPU, as you're sending instructions in the RISC-V format. Here's the problem though. If you've seen the stickers in 3026 on the computers that you work on, they use Xeons, and Intel uses x86 assembly. So the CPUs can't run RISC-V code. And that's an issue, because your operating system natively, if ran on these computers, just won't work. This is where QEMU, standing for a quick emulator, comes in. QEMU emulates all the peripherals that your operating system that you are working on will need so it can run as if it were running on a RISC-V based computer. So QEMU exposes things like a hard drive, the entropy device, RAM, and all kinds of things so that your operating system thinks it's running on real hardware. So, okay, your operating system right now, as it stands, has no way of knowing how to interact with 3026's real computer hardware. I mean, you have MMIO addresses, like those registers that are available for you are available, and you've written drivers for that, and that's cool. But what about other devices that you might need, like your hard drive? You need those other devices for a file system that needs to be stored somewhere more permanently. Games that need to have actual save states that need to be stored somewhere, not just in memory. And other cool features. Just ignore the one that I worked on for an extra credit. So this is where Virtio comes into the picture. Virtio is the gold standard of how operating systems that are running virtually, like yours, gain access to external hardware in a standardized interface. Virtio pulls this feed off by splitting communication between the operating system and the devices into two aspects, the front end and then the back end. The front end is the code that you write for this MP. Now, the back end is what QEMU does to hand this request to the actual hardware in the 3026 computer, or in the 3026, computers that you are working on. But okay, so I've just said all this, but how do we actually start working on all of this? How does the attaching work? Well, this gets on to our next section. Now we want to kind of get a high-level overview of how to use Virtio and sort of the basics of what's going on so that you can get started and just approaching this big concept. So first, it's important to understand that Virtio exposes a bunch of device registers that a Virtio-based hardware is more than likely to have. So think you're like your entropy device, and your block device that you'll be working on will have these kind of hardware registers that you're seeing here. Now, I won't go over the exact what all these device registers do. Just know that you're going to have access to these, and they're going to be really important for how your device functions. What I will say though is the first idea is when we're attaching a Virtio-based device, is that we need a way to understand what kind of features that a device supports. Now, why do we do this? Well, you can probably take a good guess as to why we do this. Because although you might be just trying to connect a mouse, for example, each mouse might have different capabilities, and you as the operating system need to know what those capabilities are and which ones you really want. Notice that in Virtio.h, we have a Virtio feat set _t. We use this data structure when we are initializing our needed features to have a couple variables. Typically, we call them wanted or needed. Wanted are features that we might want, but they're not required for operation. Needed is something that if this device doesn't have it, or have the feature that we're looking for, this won't work. Our driver will just not attach to the device. One example of this could be, let's say that you attach a disk, like a spinning disk, and a hard drive. Well, one of the needed features could be a size requirement. We want a certain size that this device is able to support. Our spinning disk, like a CD, won't be able to support that size, but our hard drive will. And so this is just one idea for why we need a feature negotiation before we fully attach the device. This feature negotiation will be present in your attach function. Now, it's important to discuss how we actually get data across in VirtIO. Now, we do this through what's called a vert queue. A vert queue is a fundamental building block of how the VirtIO protocol delivers requests to the external device so that the operating system can get the requested data or whatever it may be wanting from the external device. So really, think of a vert queue as a shared memory space between the operating system and the device. So the vert queue is composed of three parts that you'll see here. The descriptor table, which is the description of the work that the device will be doing. The avail ring, which is the work IDs that are available, and we'll talk about this in just a second. And the use ring. So the descriptor table that we'll see right here, we'll worry about this thing to the left here, but a descriptor table is going to contain these four parts. It's going to contain a buffer, it's going to contain a length of some kind, and it's going to contain flags. The buffer is going to be an address location of a buffer that exists within your memory, inside the actual RAM of your operating system or computer. Now we need this buffer because the VirtIO device needs to know where to read or write data from. And it's going to know whether to read or write based on this flag that you set here. Based on this flag that you set here, it's going to just write a certain amount of data to your device. But how much data do you want to write to this buffer? That's where you specify length. This is specifying how much data you want to request from the device. And so we'll worry about what next is in just a second. But for now, we'll focus on these three. So this whole thing you see here is a descriptor table. Each one of these sort of arrays going like this, each one of these entries going horizontally across is a descriptor. So, and typically for devices that require multiple descriptors, we store this in an array format. So, for your entry device, you don't need an array, you just need one descriptor. But for other more complicated devices, you will need a descriptor table. So now moving on to the avail ring. This is what our avail ring looks like. Now, I've sort of randomized some things here for us in this example, but we have an IDX and a sort of ring buffer here. So what is IDX? IDX is something that's going to be it's really important to the overall flow of how we get data across. IDX is the number of jobs that we have essentially done so far, but the other way to look at IDX is that when we increment IDX, it basically tells our array ring buffer, it basically tells our array ring where to place our descriptor array index within the ring buffer of the array ring data structure. So in our example, we have an IDX of 2 in our array ring. And essentially, if we take 2, we mod it by the queue size to ensure a circular queue. Then what that means is that at ring buffer location, at ring queue location 2, it will be equal to 0, and 0 being the array index location within our descriptor table. But you still might ask, what do these numbers in ring mean? These hold the location of our descriptor within the descriptor array. Not the memory address of the descriptor in the descriptor array, merely the numerical location of the descriptor in the descriptor table. So since ring 2 is at 0, what this means is that if say IDX is 2, and our device sees this IDX in the avail data structure, it will see ring 2, okay, and it goes to this 0, and it will then realize, oh, the descriptor that I need to process is going to be the 0th element of the descriptor array, meaning that this descriptor where my mouse is moving is going to be what the device processes. It's a little sort of strange to think about, but that's how our avail data structure works. It's kind of cool. Moving on to our used ring, this sort of will work a bit similar, where now instead of the device reading from our avail ring, the device will always write to our used ring. And what the device will write is the sort of descriptor like array location of what it just processed. So we'll have the index of just what we calculated. So if we just process index 2, our used ring will also be at index 2. And then it'll also include some other information shown here, such as the amount of bytes that our device had to process or had to deal with. Now, okay, I just kind of showed you a very brief walkthrough of what these data structures are. Let's walk through an example. In this example, we're going to have a case where our Virtio device, the max amount of descriptors that we'll ever have will be 1. And this will be our avail ring descriptor table. And our used. Okay, so we're gonna recap the sort of rules that we have here, and we're gonna go over the flow of the VirtIO protocol. So what we want to ensure is that we have attached our VirtIO device. The next thing we want to do is, once we've attached this device, we have to ensure that the VirtIO device can actually see the VirtQ. And you can do this by finding the appropriate register, which I will let you figure out which ones those are, and giving it the address of each of these components. So you have to give it the address of the avail ring, the descriptor table, and then the used ring. So that way your device knows where in your memory the VirtQ data structure for your specific device lives. So now what we're going to do is now we want to send in a request. What we're going to do is we're going to ensure that our descriptor table is set up. Let's say that our buffer is called buff. So for our descriptor table, we're going to give it the address of buff. And let's say that we know that our device can communicate in 512-byte packets or 512-byte blocks. So we're going to say that the length is 512 bytes, and we're going to ensure that our buffer can actually support this, transaction length. We're going to say that, okay, we're going to say that we want our device to write to this buffer. So we're going to pass it a write flag. Now, remember, in your MP, it's not just going to be W. You have to search for what this may be, and I'll leave it up to you. Now, again, next, we're just not going to worry about for now. We'll cover that in a later video coming soon. And now, after we've done this, is we're going to deal with our avail ring. So now what we're going to do is we're going to first see where within our avail ring buffer we're going to set the descriptor array index to. And in this case, we're going to look at our index. We're going to see that our index is 0. We're going to take our index, mod it by the queue size of 1, which is still 0. And we're going to set ring 0 as a result because that's what we're looking as a result of doing index or IDX mod queue size and setting that to the index of the descriptor within the descriptor array that we want the device to process. So in this case, ring 0 will be equal to 0. And then I will increment IDX after that. Now, just note that when we are dealing with a queue size of 1, we actually don't really need to worry about this modulus map. You only really need to worry about it if you have a lot more than just one descriptor that you have to worry about. Remember, not only are you, the operating system, keeping track of how many IDXs or how many descriptors that your device has processed, but so is the device itself. So the device is also keeping track of where within the array it should be accessing. So anytime it notices that your IDX is more than its last IDX that it had, it knows that, well, it's been notified and there's a job that it needs to do. So that's how it kind of is able to know where within your avail ring it needs to look at. It has its own count as well. Uh, our device. So, okay, so we've just incremented IDX. Now what needs to happen is we have to notify the device. So there is a function somewhere for this, but you essentially send a signal to a certain device register that there is a descriptor ready to be processed. And so the device will look at IDX. It'll see that, okay, 1, and presumably through some kind of logic that you gave it, it'll see 1 mod 1, and it'll go to the 0th element of this ring buffer. It'll then see that inside this ring 0 is 0, so then it'll look at the 0th element in your descriptor table array. It'll process this request. But then what happens here? How do we know that this device actually processed the request? The device will then increment the used ring by 1. So instead of this being 0, now we're at 1. And then we can check that a task was completed by seeing that if the avail ring IDX is equal to the used ring IDX. So an important distinction is we increment the avail ring IDX, the device increments the used ring IDX. So from there, then the device will say, okay, I just processed descriptor ID 0, so I processed the 0th element in the descriptor table, and I wrote 512 bytes to this buffer. There are a couple things you need to check. You need to check a certain device registers to ensure that the transaction went okay. And again, that's for you to figure out which registers those are. But this is the overall big picture of what's going on. So this is just with one item. And you can sort of extrapolate to what happens if I have multiple items here. So this is a small example of something that will be very familiar in your MP. I'll give you a hint. You're probably going to follow somewhat of a similar structure to what I just showed you for one of your Virtio devices. So that is this example. A final note I wanted to end this video on is that you may notice that as time goes on in this class, that things are going to get a little hard. You might drop your first 30 bomb or your 50 bomb on an MP, and that's okay. because I recall in MP3 for one of the checkpoints, I think I got like a 45% on the autograder. And things like this are going to happen. What matters more is that you keep trying and you keep asking questions so that you learn as much as you can. And if you do that, then around the final or just overall in the course, you are going to succeed. Remember, you're building an entire operating system, and that's something that not a lot of people can say that they've done. And remember, if you have these, if you have people like these going around and saying that they're professional programmers, then I think you can say that you yourself are doing a lot better than you think you are. Thank you for watching this video, and good luck with this MP.